Good evening, students. I'll start with the class. In the previous class, we had seen Newton's law of gravitation, which states that the force of attraction between any two bodies is G times m1 m2 upon r square. Then we had seen, suppose if we want to know what is normal gravity, then it is G m upon r square. Then gravity at a height we had derived. Okay, effect of gravity or acceleration due to gravity at a certain height, that was G1 minus 2h upon r, and due to depth was G times 1 minus d by r. Okay, based on this formula I had solved problem. Now on the height and the depth I solved. Find the value of G, or find acceleration due to gravity at a height of 400 kilometers above Earth's surface, above surface of Earth. Given that the radius of Earth is 6,400 kilometers, and value of G at surface of Earth, or means acceleration due to gravity at surface of Earth, is 9.8 meter per second. Now the moment you see acceleration due to gravity at height, you have to think of that formula for the height one. So you know that Gh is nothing but G times 1 minus 2h upon r. Then we know r is the radius of the Earth, or nothing but the distance from the surface to the Earth bed. So r is given to me as 6,400 kilometers. Height is 400 kilometers. And what else is been given? G is been given. Surface is this 9.8, and at height we have to calculate. Now this is given in terms of kilometer, or that the standard unit should be in terms of meter per second. Okay, in terms of meters. So this you can write it as 6,400 into 10 raised to 3. That is meters. Whenever you want to convert kilometers to meters, you have to multiply by 10 raised to 3. Now substitute a value here. Is 9.8. 1 minus 2 into 400 This and this will cancel. 8 8 is 64. We'll get 9.8. 1 minus 1 by 8. Cross multiply 9.8 into 7 by 8. We'll get 8.57 meter per second. This is the unit for gravity, acceleration due to gravity, meter per second square. Even if you forget, look here, same meter. Next question. At what height from the surface of the earth will the value of G be reduced by 36% from the value at the surface? Radius of earth is okay. Now what all data has been given? The height, what has been told, the height of the G will be reduced by 36% from the value of the surface. At what height? We can say let H be the height where it will be 36% reduced. This answer. So 36 means 36 upon 100. This is how we write a percentage. So reduced means what? Like from the surface of the earth till at certain height. Okay, if it is reducing by 36, how much will be the actual height? Suppose 100 was the this. Out of that, 36 is gone. So basically, the remaining out of 100% will be actual height. How much will remain if 36 is reducing? Okay. So therefore, the remaining value will be how much? Out of the 100%. 64. Yeah, 64%. So that will be 64 upon 100. So basically, what they are trying to say is your height, this will be 64 upon 100 times from the surface. So this is the data. Our radius of the earth is 6,400 kilometers. One thing you can do is, suppose if your teacher is asking to write answer in terms of kilometers only, then you can keep like this. Okay. Now if you are substituting in kilometers and after finding what is the height, suppose if you are calculating height, that will also be in kilometers. But if you are converting into meters and writing, then this will be in meters. So whichever way up, how your teacher is using. So if you are using substituting directly 6,400 as this, then make sure then you are writing this also in kilometers. If this you are using in meters, into 10 raised to 3, here also into 10 raised to 3 will come. So use the value R we know, that is 6,400, GH also we know. So GH will be G times, same formula. Okay, now we have to find the height, no? So directly we will not be able to use 1 minus 2h. So this is the first one. One second, no? Okay. Both the values will not be able to get. Suppose if I use 1 minus 2h upon r. There are two unknowns. GH you can directly substitute, suppose 64 upon, yeah, it will. So this will be 64 upon 100. This will be G. Both the sides there will be G. 1 minus 2h upon 6. You can use. So now G and G will cancel. So instead of GH, I have used this form. This value is substitute, G and G will cancel. So this will be 64 upon 100 is equal to 1 minus. So I have used in terms of kilometers only right now. So later answer whatever is, that also unit I will write in terms of kilometers. So what you can do, this value you can bring this side. Now cross multiply. So this will be 36 upon, can do like 64 minus 100 upon 100, which is minus 2h upon 6,400. Both the sides minus minus will cancel. The h you keep there only, remaining terms you bring other side. What I did, this is in the denominator. If I am taking up, it will go to the numerator. This is in the numerator, so this will come down. Okay, will be 80. When you multiply, that much kilometers will be your height. Next one, final law based on the depth. Assuming the Earth to be a sphere of uniform mass density, how much would a body weigh 800 kilometers below the surface of the Earth if it weighed given the radius of Earth r equals to 6,400 kilometers. Assuming that the Earth to be a sphere of uniform mass density, how much would a body weigh 800 kilometers below? So the depth given is now 800. Below means, where is it? Below the Earth's surface. Depth will be 800 kilometers. R is given as 6,400 kilometers. Weight is given as 360. You know that weight is nothing but mass into gravity. Now the formula which we know for the depth is Gd is equal to G times 1 minus D upon R. Now the weight, finally weight also has been asked. Okay. Now we have to deal something in terms of weight. Now there is mg here. So same way there will be mg. If we want mg, what we'll have to do? Nothing but multiply by m on both sides, because we know only mg is 360. G we would not know. Or you can take the other way around also if you get confused. What is G? Nothing but 360 upon m is it. You can take like this. So now GD is 360 upon m, 1 minus, what is the depth? 800 upon, both are in terms of kilometers. Kilometer will anyways cancel. Even if you had converted into 10 raised to 3, both would be 10 raised to 3. It would cancel and you would finally get this one. Now this M we will take this side. So then 360 into cross multiply 7 by 8.
Yes, can see.
Okay, so cross multiply you'll get this. So approximately we'll get 350. Now what we have got, finally if it was only GD, if gravity due to depth was asked, it would have been 315 upon M. But finally weight has been asked. This is nothing but the weight also. Okay, M into G, we know it is weight. So this is nothing but weight at what depth? Weight of the body at depth. And unit of weight would be Newton. Mass is in terms of kgs. Weight, please understand. Mass, this is M in terms of kgs. Weight is always mg Newton. So we always have that concept wrong whenever we say I weigh 50 kgs. So that is the mass into gravity. Then it would be in terms of Newton. So basically what we say is, when I say I weigh 50 kgs, it tells me my mass, not exactly weight. Weight would have been 50 into 9.8. So this is the weight of the body at depth which was been asked to find. So that is how much he weighs below the surface of the earth. Next topic, that is gravitational potential. Based on the question papers, the problems at the end of the chapter, I solve all mixed problems. This is gravitational potential V. Now we know that there is, suppose this is the earth. Now gravity of earth lies within certain limit. Okay, till some point if you go through a ball, it would definitely come down. Okay, so this gravitational effect is applicable up to certain area, this much. So this is also called as a gravitational field. This area would be called as a gravitational field. So what is gravitational potential? Nothing but I'll give the definition first. Means if I want from the earth, if I want to take this, there's an object, suppose over here. I'm taking this object somewhere far away till infinity. Okay. So how much work, how much energy or how much work I will have to do to take this body from here till infinity against the gravity, because gravity is trying to pull it down. But I have to put some force, some energy, some work to take this point from here to infinity. So that is called as a gravitational potential. That is the work done to take this from here to infinity. So gravitational potential at any point in the gravitational field. Gravitational field is, I told you, the area till where gravity works. Is defined as the work done in moving a unit mass. Unit mass means mass of 1 kg from one particular point to infinity. Just for understanding, if you want to draw the no need to this for exam fast directly definition, but if you just want to know, this is your earth and suppose if there is this, so this is 1 unit mass. The work done to take this to infinity is called as a gravitational potential. Infinity means very far away from the earth. So the formula of potential is, it's always negative. Why? Because the work is done against gravity. Gravity is trying to pull it towards himself and you are trying to take it away from it. That's why the answer will be in terms of negative. Where G is nothing but gravitational constant. That is, you know already it is fixed. G is 6.67 into 10 raised to minus 7. R is the distance to be traveled or distance from the center of whichever planet and the point to which is been taken. M will be definitely the mass of the planet. Why this M is gone? Because we are taking unit mass. The formula is nothing but the force Gmm upon R. But mass we are taking of the smaller one is 1 unit. But basically, it's only the mass of the planet which is left. Same is the mass. So some points to write for gravitational potential. Its unit is joules per kg. It is always negative. It is a scalar quantity. No need of direction, which direction you are taking. Whether this side, wherever, there is no vector involved in this. So it is a scalar quantity. Potential will always increase, okay? It increases as one moves from the point towards infinity. As we go towards infinity, the potential keeps increasing. Increasing means what? Basically, it's in the negative side. So, but finally, I'll write this point and then I'll explain. At infinity, it is maximum. That is equal to 0. It goes reverse actually. So if it was something minus 1000, then it would become minus 900, 800, minus 600, minus this, okay, and then it would go to 0. It's like minus 900. Although the numbers are decreasing, but you know that minus 700 is bigger than minus 900. So that is why we say it is increasing. Although the number is decreasing, but because it is in negative, we have to say it is increasing. Every small value, like so minus 10 would obviously be having a higher value. So this is a bigger number than this. And what is the maximum value? Then it would reach 0. Numbers are decreasing, but the value actually, it means it is increasing. Potential is increasing. Suppose if you are exactly at the surface of the earth, then V will be minus Em upon R. R is the radius of the earth, only this much distance, no, exactly at surface. Okay, next term is gravitational potential energy. You know, it is work done is almost same as energy. So gravitational, it is just how to express it, how much capacity it is. Gravitational potential energy means after taking it to some point, after you store it at a certain height, then it is called as a potential energy. That is nothing but amount of work done in moving the body from that point, whichever point it exists, to infinity against gravitational force. It's basically the same thing. Only when you store it, means it's held on, it is kept stored, then it is the word used is potential energy. Gravitational potential and potential energy basically same. Only thing, the formula anyways is same. G will be this instead of G, we will use it as U instead of V. Sorry, the letter U for potential energy. Looks confusing otherwise. And draw it like U. Okay. Now only thing here it is not infinite. The difference here is mass is not 1 kg. There it was unit mass. Here it can be any mass, 10 kg, 20 kg, it doesn't matter. Potential, just normal potential would be what? Taking 1 or 1 unit. So gravitational potential, your mass is 1 unit. and gravitational potential energy. Mass could be any. Here it is fixed 1 unit. That's the only difference between potential and potential energy. So that's why this m will be smaller. There what was happening? M was 1, so that was gone. So G is minus, sorry, U is, yeah, U is minus G M. Now we will derive the derivation of gravitational potential energy. If it is not done in your college, you can keep it up. Now suppose if we have Earth or any planet, you can say, and the radius is r, and if you have an object at this particular point of mass m, let that point be P. Now what I'll do, I'll put some effort and try to take it till A, point A. And then a small distance, I'll take it to point B. This is almost at infinity, okay? And then little bit further. From here to here, what is R I told you? This is from the center of this to this. Draw it in a straight line. This is point P. Draw it straight up. This is R. From here to here, how much ever efforts you are taking, that is X. And small distances, Px. This much. M is the mass and O will be the center. This is the diagram. So basically what it is, this is a planet. There is one small object of mass m over here at point P. So what am I doing? From point P, I'm trying to take it to infinity. After taking it to infinity, little bit extra, I'm taking it further. Right? Consider Earth as spherical body of mass m and radius r. Right? Let m be mass of small body look at point P. Such that distance OP is equal to r. such that this distance OP is equal to R. Now, as per Newton's law of gravitation, we know that definitely there is a force which is acting between these two bodies, the Earth and the small body, that is given by G m upon R square, the distance between them, because m1, m2 it is. M is of the Earth and this mass is of the small body. Now we have to calculate the gravitational potential energy. It's nothing but like work done in moving from here to here. So what we'll do, move mass m from point P to infinity at point A. Distance covered or such that you can such that OA is equal to X. So what will be the force now? After going here, the body force will be same formula, but now the distance has changed. This will be X square now. You can mark this as equation 1. So this is basically at point P. And this is basically at point A. So at point A, what is the distance between the two bodies? X. That's why it becomes X square. Rest all everything is same. Now what I'm doing from point A, little bit further I'm taking to point B. Let's, or you can say further, move M from A to B. The small distance dx against the gravitational force. So I'm taking it from here to here. So we know that work done is nothing but force into displacement. And write in words if you want. Work done is force into displacement. Now what we are doing? We are doing a small distance, so small work done. Force into small displacement. What we'll do, we'll use dW now instead of W because it's small work. Force anyways will not change, so that we are using minus because we are doing it against the gravitational force. And small distance or small displacement is dx. So put this F over here. At point A, what was this? This is d m upon x square dx. Put this value over here. From where I got? From equation 2. Value of F. Now whenever you know small work done, if you want to find total work done, you always integrate it. I told you, anytime you want to know entire work done, then you always make it small pieces. Like everything gets divided into small pieces. Because this is not going in a straight line, not necessary. Now I've drawn the diagram as a straight line. But what while taking you could go like this, like this, like this. We directly cannot calculate. So what all the this dx is always divided into strips from starting till the end. And then what is been done? Integrated, added all those small values. Like small work done, small like this. And then final total work will be sum of all the small works. Therefore, total work done will be in moving the mass from R to infinity. Total is sum of all the small work. From where to where? From R to infinity I'm taking. From R to infinity. So from here to here. Now put the value of dW here. Big work done is nothing but addition of all small work. That will be minus CMM. These are all pure numbers because gravitational constant means you already know the value 6.8. Then mass also of the earth we would know, that is also a pure number. This also you would know, that is not changing. These are all fixed values. So any pure number we can always remove it out of the integral sign. So remove everything out. So minus GMM are gone out. So what remains is 1 by x. This infinity is over here. Huh? So I have to find integral of this. So anything in the denominator I directly cannot find integral. I'll take it on top. So minus GMM. This is minus 2 it will become. Now it is in the form of integral of x raised to n dx. The value of n over here is anyways now minus 2. What is the formula I told you for integral? Anything this and this is matching, then the power will always be n plus 1 upon n plus. This is the integral formula. So as per that logic, it will be x raised to minus 2 plus 1 upon minus. N value is minus 2. And then we put a box and write this outside. Answer is x raised to minus 1 upon minus 1. And as numbers you can always take it out. Minus and minus will cancel. So g m x raised to minus 1, I'll take it back as 1 by x. I'll take it back to the denominator, it will become x raised to plus. Now what we do, always substitute the higher limit first. Wherever there is x, we'll have to put this minus this. 1 by infinity is always equal to 0. Overall, this is the answer. We know that work done is equal to potential energy. So therefore answer is U is minus E and M upon R. So basically what is this? It is nothing but the this gravitational potential, formula of gravitational potential. And what is this? Nothing but the mass of the small body. So you can also express another formula, gravitational potential energy is nothing but gravitational potential into mass. So it's basically U is nothing but V into M. This is also one formula, this is also you can write. So based on this, there is another formula which you can say total energy if you want to know. Total energy of a body in a gravitational field. Total energy is, you know that it's nothing but kinetic energy plus potential energy. Kinetic energy formula is what? Half mv square. And potential energy just now we saw is this formula. Like basically there's a plus sign, then minus. Okay. So this is about the gravitational potential and the potential energy. Next is the topic satellite and something called as escape velocity. Theory part I will give you, I'll share the slide. Just listen to this. Satellite is definitely, you know that any object, you know this is the Earth. So outside the Earth there will be orbit. Okay. Any object which revolves around the Earth in a circular orbit, okay, under the influence of the gravitational force. If gravitational force was not keeping it holding, it would fly away in the universe. Okay, you can imagine this moon. Moon doesn't go anywhere else. It just keeps roaming around revolving around the Earth. Why? Because the Earth is keeping it on track because of its gravitational force. If gravitational force is not there, either the moon will come and collapse on the Earth, or it would go far away somewhere in the space. It would not be revolving around. So this is under the influence of the gravitational force. Now this is what a natural one. That is a natural satellite which already exists. Now humans have already made some satellites, okay, from the earth, then this send so that it revolves. So there will be many orbits. So artificial ones could be there or natural ones which already exist. So satellite is basically any object revolving around the planet under the influence of gravitational force without consumption of any energy. This fellow doesn't have to put his energy to roam around. Automatically it's roaming around, revolving around because of the force of the gravitation. Moon is not generating energy to revolve. Okay? It is going under the influence of the earth. So this is what you have to know. Now how, suppose if you want to now send some artificial satellite. So obviously we just simply don't sit on the earth and throw it just like that. The this what is used to transfer a satellite from the earth to this outside the orbit or inside whatever that revolving orbit, we use a rocket. The device which is used to transfer a satellite from the earth to the orbit is a rocket. So there are various stages for the rocket. So what we do, we use a rocket. At the tip of the rocket we keep a satellite. Okay, suppose so the satellite would be here. Then we ignite, so it would go here at some point. So this will be your first stage. So it is been ignited. Now after the first stage, what happens? This is now if you have seen, our rocket will travel exactly vertically up. At certain point, no, then the rocket will. If this is this satellite, it would change exactly in the horizontal direction. So this is the second stage. Okay. So initially, what is happened at the first stage, a rocket is ignited, and then it goes to a certain height. So after a certain height, what happens at the second stage? The first stage gets detached automatically. Means inside there is a system. What happens? That system control mechanism is there. It's already programmed. So the moment it reaches after a certain height, that whole system changes and makes it to a different direction. That is in the horizontal direction. Now again there's a ignition. So it picks up speed in the horizontal direction now. So after again it travels to a certain distance, and then what happens? The rocket detaches itself or it collapses automatically, crushes, and then what remains is only the satellite, which would be in the whatever in the range of this. So basically it would be like this, and it will go horizontal. The moment it reaches, it detaches, and then it starts revolving. So these are your stages. Now it's very important at what velocity it has to leave. Now imagine if the velocity, that velocity is called as a critical velocity sometimes. Simply at any speed you cannot say. There's one particular speed. There are three cases which can happen. First one is what? If this velocity is very less, this horizontal velocity is suppose very less, what will happen? It's not enough to keep it there, so it will get pulled by the gravitational force, and the satellite will come back and fall on the earth. Okay, if the speed of this satellite or the rocket is very less compared to that particular velocity which has to be there, then it will fall back to the earth. Second case is what? If it is too high also, what will happen? The satellite will go out, rocket will go outside the orbit of the earth, will go in the space. That is one another case. And the third case is when exactly that horizontal one should be equal to your critical velocity, then only exactly of the orbit velocity, then it will remain in the orbit. So three cases, and this is less than this, so it will fall back on Earth. In the second case is exactly equal, then it will revolve. And the third case, when it is greater, so it will escape out. Okay, move outside the Earth. So I'll just share the slide. I'll just read it out. If you want, you can later copy it. I'll put it on the group also. So this is a basic definition of a satellite. Well, you can write later. I'll just read. Any object revolving around a planet under the influence of the gravitational force without consumption. I told you, moon is not generating its energy. So you can think of that. Without consumption of any energy of its own, it is just under the influence of gravitation. That's why it is moving. It is not producing any extra energy. You don't need any fuel for making the moon revolve. It is revolving on its own. Now, the steps involved in projection of a satellite. Projection means what? Sending a satellite on its orbit. From the Earth, we are projecting, means leaving from the Earth to a certain height. So first step is a satellite, whichever has to be sent, is kept at the tip of a multi-stage rocket. Why I'm saying multi-stage? I told you it has many stages. It changes its state from one stage to another. So first, what they do, they keep a satellite on the rocket, at the tip of the rocket. Initially, at the first stage, what they do? They ignite the rocket. So what happens? The rocket rises to a desired height. Desired means whatever fixed height you want to send it above the surface of the Earth. Okay, so this is your first stage. Now the second one. So at once it reaches the desired height. At this height, the first stage of the what rocket gets detached. Means it enters the second stage automatically. No one has to do anything. It's already programmed inside. And the rocket control mechanism, whatever is controlling the rocket, it rotates the rocket in the horizontal direction. So that is your second stage. Now what happens in the second stage? Again, it has to start moving in the horizontal, so it needs some energy. So what happens? Second time again there's ignition. So now ignition starts again in the second stage. And because of that ignition, under its effect, the rocket is pushed in the forward direction in horizontal one. So it has to gain enough velocity to start moving in the horizontal. So it's like you're moving and then you take a sharp turn in the horizontal direction. So it needs some energy to move in the horizontal. So that's why that ignition happens. Then at the second stage, what happens? That is also gone now. Second stage is also detached and the satellite is kept at the tip of the rocket. Now what happens? It is at a very high velocity. So this velocity is called as the horizontal velocity. Now based on this, the horizontal velocity has to be equal. It has kept equal to the critical velocity. So that what happens, the satellite should remain in the circular orbit of the Earth. The seventh point is, for the circular motion of satellite is necessary. Centripetal force is due to the gravitational force. Okay, means what? It should be under the gravitational force of the satellite and the Earth, because it will not have any more energy left. it loses all its energy in moving in the horizontal direction. After that, whatever energy is there is under the force of gravity. Now the different possibilities. The first possibility is if the horizontal velocity of a rocket is less than the critical velocity, then the satellite describes like in a parabolic path. The arrows are shown in the diagram is there, like parabola types. It will come back to the earth, falls back to the earth. Now second case, if both are equal, then what happens? The satellite is established in a circular orbit. So total radius of the earth plus how much height it goes up. So total distance will be from the center of the earth. If you are calculating, it will be r plus h. And the third case is when it is greater than. So it will move out of the orbit and then revolve in some elliptical orbit. So that is not exactly the Earth's orbit. Outside the Earth, which is useless. Okay, the same thing I'll put it in the group. If you want, you can write. If you have understood, you can write in your own words also. If this is your Earth, this is a circular orbit, which is the Earth's orbit. If not, then it would be going right like this in space, which is none of others. It's like this, elliptical. It is outside the even gravity of the Earth. So that critical velocity is called as the escape velocity. What is it's nothing but the minimum velocity with which a body should be projected from the surface. Projected means I told you should be sent, okay, fired or ignited from the earth and sent up. Projected from the surface of the earth or surface of any planet so that it escapes from the gravitational field of the planet. I'll explain this. Just write first. The minimum velocity with which a body should be projected from the so that it escapes the gravitational field. Escape velocities of certain planets. So escape velocity of Earth is actually around kilometers per second. Now what happens is, suppose if this is Earth. Now you reached here. You are suppose having lesser one. Suppose if you're having 11.1 velocity, the speed of your rocket is 11.1. So what will happen? It will reach her and it might stop exactly at this. It is not sufficient to overcome this escape velocity. So this what happens, Earth this is more than what is you're trying to escape. You are trying to move at 11.1, but Earth is trying to pull you at this much speed. So you have to try to escape. Then in this case, you will come back on Earth. If you want to escape, then it has to be either 11.2 or more than that. So 1 like that. And so on. So this is the minimum velocity which you need. If you are less than this, you will fall back on Earth. This rocket will fall back, even if it's like 11.119, whatever it may be. It has to be minimum approximately that much. Okay, so I'm reading it again. So the minimum velocity at which the body or that rocket, whatever, should be projected from the surface of the planet so that it escapes the force. Otherwise, he will pull the rocket back to the Earth.
Teacher, kilometer per second.
Yeah, kilometers per second. Otherwise, you can write like 7.2. That is time. And just derive that. Similar to the previous one. Same diagram, okay? Which we use for potential, no? Same diagram. Same diagram we have to use. Now only thing that r will not be there, so you can directly start a. So this is suppose distance x. And then you are moving it to small distance b. Same thing you have to write starting. So this is derivation for escape velocity. Consider a planet. Like the different planets would have different escape velocity. Consider a planet as a uniform sphere or as a spherical body of mass m. This much is r and radius r. Right? Let m be the body. Let m be mass of the body at distance x from center of the planet. Or basically you can say such that OA is equals to x. So therefore what will be the force of attraction between them? G m upon x. Now move m from point A to point B at small distance d. Do you know that small work done is nothing but directly I'm writing now, work is forced into displacement. So small work will be forced into small displacement. This will be dW F into small displacement will be dx. Now put this value of F over here. Where we got from 1. Value of F we have substituted. Now this is small work done. So total work done will be moving the object surface of Earth. Definitely now we cannot suddenly start from any point P over here. Rocket obviously will start from the surface of the Earth only. From the surface of the Earth. So at what height it would be here? From whenever you measure distance, you are measuring from the center. So here it will be R now. Surface of the Earth here. Okay. It is R to infinity. So total work done is nothing but addition of all the work from surface of the Earth till wherever infinity you are taking. In the previous one, we were taking somewhere in the middle. Okay, so that's why we have taken small r. The total distance we have taken r. Now this time we are taking from the surface of the Earth. We are launching the rocket, you can imagine. So it will be from this much distance from the center we have to measure. So it is at r, and then we are taking to infinity. Now substitute this value here. Same like previous problem, remove everything out. What remains is basically 1 by x square. Take this on top. Here we have not taken minus because we are not calculating potential. In the previous derivation we had used minus y because we told that potential we have to always take negative. Here we have taken normal positive. This will be x raised to minus 2. So we know that integral of this is x raised to minus 2 plus integral sign will go now upon minus 2 plus x raised to n plus 1 upon n plus minus 1 will come out and everything will become minus. Minus 1 I'm taking down, so it will become 1 by x. Now substitute. 1 by infinity is 0. Minus into minus will give me plus. That is your work done. We all know that work done is nothing but same as energy. Now which energy will be there? We are launching the rocket. So whenever the rocket is moving, it will be kinetic energy. Kinetic energy is same as the work done. What is the kind that is of the projection? Means kinetic energy to move the rocket. When you ignite, definitely you need the energy to move the rocket. So that energy, whatever you are using, is nothing but what work you are doing. That's exactly your work, no? To move the rocket up. So what is the formula of kinetic energy? Half mv square. What work done you got? Gmm upon r. Now which velocity it is? We are calculating escape velocity. So just have to write the letter E, because with that only velocity it has to go. Otherwise I told you, if it's less or greater, it would be less, then it will come back to the earth. So if you want to calculate this, take rest of the things on the other side. 2 will go up and m will come down. R is already m and m will cancel. V square is V will be root of. This is your escape velocity formula. This is when you know gravitational constant, mass of the earth and the radius of the earth. You can also express in terms of acceleration. Escape velocity in terms of gravity. We already know that this is the formula for gravity. R square is there. Out of this now, what I will do? This R square take up. What is the value of Gm? Gr square. Just put it here back. This formula I already know. Gravity is what? Gm upon R. Now R square I have written here. So basically I want to introduce this acceleration due to gravity in this formula, because I want to know what is escape velocity in terms of gravity due to acceleration. So to introduce, put value of Gm in whatever equation 3 if you have written. So what will happen? This is the formula. What is the value of Gm? Put Gr square here instead of Gm. On R will cancel. So answer is this small g. 2 in terms of gravity due to acceleration is so on. And suppose if you want in terms of last one, if you want in terms of density, and directly give you the formula. So this density is given and you want to calculate escape velocity, and this is the formula. 8 by 3 pi e rho r square. Rho is the density. So three ways you can write escape velocity. Unit of escape velocity, velocity no, meter per second. And in that case, you have to use radius in terms of meters. Let's stop here. Next class we will see what is orbital velocity. We will derive formula for that.